Good morning, Bears. We are continuing thermochemistry. You got a video to watch last Friday, and we're going to expand as much as we can on this. There are lots of pieces to this, and so we're going to try to keep it as simple as possible. Make sure I give you the basics of this, so that if you go into another class, another science class, or when you get to college, you take chemistry, you are at least familiar with a lot of these terms and words that are in this unit. All right, so before we get into calculating pieces of thermochem, there are some basics that we need to, like the foundation that we need to start from. And we've talked about a lot of this before, talking about exothermic reactions and endothermic reactions. An exothermic reaction is a reaction that is releasing energy. All right, so exothermic reactions release energy, and endothermic reactions absorbs energy. So let's look at what that looks like. So in this graph that we see here, this is what we would see, when chemical reactions occur. We can basically graph out what is happening, where the reaction is requiring energy, if it's releasing energy or gaining energy. We use potential energy graphs to look at the changes of energy from the reactants to the products. That overall energy exchange is key when we're looking at, we said at the beginning of the year, for example, that we said matter cannot be created or destroyed. I can't have a chemical reaction with a gold element or a gold atom and it magically disappear where gold is nowhere in the product side. That's the same thing with energy. Whatever energy we start off with reactants also needs to be somewhere accounted for in the products. Now, that doesn't mean that the reactants in the products are going to have the same energy. For example, if we have this exothermic reaction, it's going to release energy. So some of the energy from the reactants is going to stay with the products, but then some of the energy is going to be released out into the environment, into what we call the system. So I just want to try to, let's break this down a little bit more. Potential energy, what we're looking at here is the overall energy of what we're graphing or what we're analyzing. So let's take a look at this graph right here. We have the reactants. The reactants have a certain amount of energy that are stored within their bonds. So for example, if I had hydrochloric acid, HCl, in this bond that keeps them together, there's a certain amount of energy there. Now, if it undergoes the reaction, let's say with sodium hydroxide, well, now we have another component or another reactant that also has a bond, right? The sodium is bound to the hydroxide. So there's more energy that's stored there. That's the energy that we're essentially looking at as far as stored energy of our reactants. All right, that's the first part of the graph. Okay, now when you mix two things together, sometimes this happens, not all the time. Sometimes energy is required in order to get those reactions to occur. You can think of this as like when you're cooking, right? I can add I can add a, let's see, a hamburger patty to a skillet. But nothing is occurring initially, especially if I just turned on and I didn't let my pan heat up, and I just barely put it in the pan, barely turned on my stove, and I put the hamburger patty on there. You're gonna see that nothing is occurring. After some time, you start to hear it sizzle and pop and all these sounds. And that's when you know that that chemical reaction, that the molecules of the hamburger meat are starting to change and release energy, and so that's when the reaction begins to occur. So here, the reason why I bring that up is because there's usually this element of activation energy, this energy right here. The reaction doesn't actually occur. We don't actually start seeing new products until we reach this point right up here. It's not until we reach this, the apex of the graph, where we begin to see products being made. So what's happening all right here? Well, the reactants, in our example, hydrochloric acid and sodium hydroxide, are beginning to separate. They need energy to separate from each other. So we have to get that hydrogen off the chlorine and that sodium off the hydroxide in order for them to rearrange themselves and actually have a chemical reaction. So activation energy is different for different reactions. Here we see in the exothermic reaction that not a whole lot of activation energy is needed compared to our endothermic reaction that requires a lot of activation energy in order for the reaction to begin occurring. So you just need to understand that, and this could be really, really small. It could be almost nothing there. But there's always this element where, or this part of the graph when we're looking at potential energy diagrams, that activation energy is the energy that is needed, that is needed for the reactants to get going and moving towards actually causing a reaction. On the downside of this graph, we see that we have this slope, and it begins, and in an exothermic reaction, it's going to drop quite a bit. Within this time period, because, I'm sorry, I need to go back and point out, the reaction progresses over time. So the y-axis is energy. The x-axis is like, if I started the reaction right now, where is it going to be over this period as the reaction is occurring? So I apologize for not explaining that in the beginning. So on the downside of this graph, what's happening within the reaction is bonds are still being rearranged and formed. And notice that in an exothermic reaction, where we started off with energy, way up here, when all the products are finally made in that reaction, we end up with our energy way down here. And it can be identified by this little line right there. That is the total difference of the energy of the reactants to the products. So and it doesn't include the activation energy, because the activation energy was what was used to get the reaction to go, but that's not necessarily the same amount of energy that will be utilized in making new product. So if we actually had a number here, let's say we started off at 400 kilojoules of energy, and let's say that our final product's potential energy is somewhere around 200 kilojoules of energy. In order to calculate total energy exchange, we do products minus reactants. So we would do 200 kilojoules minus 400 kilojoules, which would equal negative 200 kilojoules. What does that negative mean? It means that energy was lost. Energy from the reactants to the products was lost to the system. Let's take a look at the potential energy of an endothermic reaction, a reaction that's opposite. Here we have our potential energy of our reactants starting really low. And we see that as the reaction begins to occur, it's a lot of activation energy needed to get this to get going. We call this up here, where at the very top, the activation complex. At the activation complex is where we begin to see some product being formed. And remember, going down, the elements are just kind of settling and with their new, with their new form. And so the energy is beginning to, that activation energy is beginning to go away because not as much is needed. By the time we get to the end, we have our products, all of our products that would be made from this reaction occurring. Now, in this particular graph, notice how the potential energy of the reactants is much lower than the potential energy of the final products. So this is a slightly different situation where the activation, some of that activation energy that was needed to get the reaction to begin actually stays with the products. And so this is energy that was kind of added to these new products, I should say. So in this case, we could still, let's say we have our reactant starting at, we'll say 200 kilojoules. We're just going to go opposite the other way. 200 kilojoules of potential energy for our reactants. And let's say that our products end up having potential energy of 300 kilojoules at the very end. Using the same formula that we used up top, products minus reactants, we can look at this potential energy graph and say, okay, 300 kilojoules, because this is the energy of our products, minus our potential energy of our reactants, which we said was 200 kilojoules, is a net difference of 100 kilojoules. That means 100 kilojoules of energy was added to the system or absorbed into the reaction. And so because energy was absorbed, we call that an endothermic reaction where energy was taken in. Just to quickly expand and review real quick, endothermic, exothermic, all chemical reactions can be identified as exothermic or endothermic. Sometimes the changes in energy is so small that unless you have this highly sensitive thermometer, you wouldn't even notice the changes. Sometimes the reactions are so drastic that it's very obvious. Exothermic reactions release a lot of energy, and we use exothermic reactions in things like in nuclear reactors. That heat is released using nuclear elements. The heat is released as we get them to react Water is used to cool them, and that creates a lot of energy that can be stored and then utilized um, uh, in for whatever electrical purposes that we need it for. And then endothermic reactions can be drastically cold. Now here's the thing, exothermic reactions get hot. Endothermic reactions get cold. And the reason that the endothermic reaction, this always gets confusing for students because they're like, well, it's absorbing energy, so wouldn't it get hotter? That's not necessarily the case. If I have a beaker where a reaction is occurring, and let's say it's an endothermic reaction, the reaction is absorbing energy from the outside. So energy is going in. Well, when energy leaves a space, you're left with it feeling cold. And so, because that energy is going into the actual reaction, you're left with minus energy here, minus energy over here on all sides. And so, what you're left feeling is cold. So, that's just kind of a little. It takes students sometimes a little time to wrap your mind around that. Okay, so real quick recap on just looking at potential energy diagrams. Potential energy diagrams are used for us to look at energy exchanges in chemical reactions. On the y-axis, we have the potential energy, and then on the x-axis, we have the reaction occurring over a period of time. Potential energy diagrams show the energy stored of the reactants all together combined. There is an activation energy that is required in order for the reaction to occur. So we see this little going up sort of thing. And then at the very end, on the other side of that, we have the potential energy of the products. So this is as the reaction is occurring. As those elements are breaking apart and rearranging themselves to form the products. We can take the final energy of the products, subtract it from the initial energy of the reactants, and get an overall change of energy. That overall change, if we get a minus, tells us it's an exothermic reaction. The energy was lost or released. Where on the other side of an endothermic reaction, if the potential energy of the products is higher than the potential energy of the reactants, we end up with a plus exchange of energy, and therefore we had energy absorbed, and we call that an endothermic reaction.